In the previous lecture, we started looking for a convenient basis for this symmetrized tensor product space HSN. So if you remember, we start with a basis. We start with an orthonormal basis, mu j, for our single particle space H. This was step sort of 0, or let's call it step 1. And the first idea to build a basis for this Boson-Fermi product space HSN is to build a basis for the space of n distinguishable copies of these particles. That was the next step. And then the idea is just to hope that this the basic idea is just to hope that that's somehow a basis for the space we want. Now, we already know that we're in for trouble. The problem is, of course, is that this space here is presumably got a different dimension to this space here. I mean, before we talk about infinite dimensional spaces, let's just talk about finite dimensional Hilbert spaces. This space here, if H has dimension d, then this space has dimension d to the n. And then if you apply a projection to a space, to any vector space, unless that projection is the identity, it's going to project onto a lower dimensional space. So these guys here, these vectors here, at worst, an over-complete set of vectors. But at best, they might be, almost a basis. It might be that each one of these vectors is either completely zero, just vanishes, or is a basis vector for Hs of n. And in fact, sort of remarkably, that latter possibility is the one that actually takes place. What we're going to do now is actually prove, we are going to prove that this latter situation does take place, namely that PS either annihilates one of these things or it produces a vector which will be proportional to a basis vector of H of S of n. And then I think the rest of this lecture will be concerned with normalizing these vectors. So it's not, when you apply a projection to a vector, there's no guarantee that if the vector was normalized before, that it remains normalized after you apply a projection to it. So if we want an orthonormal basis, we'll need to normalize the vectors. That requires a little combinatorial argument. And then, to finish off for today, we will work out the dimensions of this space HSN. That requires a slightly more involved combinatorial argument. One that seems rather painful, in fact. So working out the dimension of HSN is a very painful and difficult combinatorial problem. If you look in some textbooks, it seems quite painful the way they do it. I've found what I think is one of the most compact proofs of the dimension of this space that I hope to show you by the end of today. All right, we're going to prove something about these vectors here. This is the objective for today. Remember we introduced this idea of an occupation number. You look at one of these bases, these product vectors here, and you compute these numbers n mu, n mu1, n mu2, which is just counts the number of times the symbol nu appears. So we introduced this idea in the previous lecture. So suppose we have a vector mu1 through to mu_n, product of mu1 through to mu_n, and it has these occupation numbers, blah. And suppose we have another one. With different occupation numbers. Then, this is probably the most important tiny calculation in this whole business. If these numbers, if this list of occupation numbers here is different from this list of occupation numbers here, then these two vectors here are orthogonal. That's what we're about to show. Good. If this list of occupation numbers n is not equal to the list of occupation numbers n prime, then these two vectors are orthogonal. So I'm using this notation here, n bar, n underline is just the vector of these occupation numbers. It's an infinitely long vector if Hilbert space H is infinite dimensional. That's the claim, that these two vectors are orthogonal. And the way to establish that claim is just to note, first of all, is that PS is a projection. Step one. So PS is a projection, so PS squared is PS. And then what is PS? Well, we have a formula for it. PS is given by this. Now it's been brought to my attention that it probably makes more sense to define u of pi, not the way I've been doing it so far, but rather this way. Because this makes u of pi into a proper representation. The way I had it done before, with the minus ones down here, it was an anti-representation or a dual representation. It was not as natural a way of doing things. So just in your mind, replace pi with pi minus 1. Luckily, it didn't make any difference up to now. Right, so we know we have a formula for P of S. Good. And that means that this inner product here, let's call it star, is, well, we just substitute this into here. And then we analyze each term, right? There's n factorial terms and they all look like this with some factor in front. Now if we could show that every one of these was 0, then of course we'd know that that inner product there was 0. Let's just think about this. So if they have the same occupation numbers, the same number of 1s, the same number of 2s, the same number of 3s, and so on, then it's easy enough to conclude that there are non-trivial permutations which allow this vector to have a non-zero overlap with this vector here. But what, for the sake of argument, if the number of 1s in this vector here is different from the number of 1s in this vector here? Well, then no matter what you do to permute these things, there'll always be a 1, an extra 1, say, if there's 3 1s here and only 2 1s there, then there's an extra 1. And that 1 has always got to pair up with something that's not a 1, so it's always 0. So that is equal to 0 if n bar is not equal to n prime bar, underline. And poof, that's the end of the proof, really. So we learn that these things are orthogonal if they don't have the same occupation numbers. And it turns out that's basically it. That's the whole content of this construction. We've got to be a little bit careful now about normalizations. But that's it. Of course, there's some overcounting we have to deal with still. Some vectors will have a non-zero overlap. In particular, if they have the same occupation numbers. Because I've just, this line down here is essentially an if and only if with some extra quantifiers. What it says is that if the basis vector mu prime and the basis vector mu have the same occupation numbers, well, yeah, there are permutations which have a non-zero overlap here. And that leads to vectors which have got a non-zero overlap up there. So we want to deal with this overcounting. And that's what we're going to do in a second. We'll just do it all at once. I'm now going to write out the basis for HS of n. we're going to write our basis vectors in terms of the occupation numbers. And these are in turn defined as some scalar multiple by these projected basis vectors. So for this to be a well-defined definition, we need that if two vectors have the same occupation numbers, they're in fact the same vector. And we need to work out this CS of n. Firstly, so is it well defined as a definition? Suppose we have two basis vectors with the same occupation numbers. Like, what's an example? I'll do a quick example here. Okay, suppose we have two representatives for this same vector n bar. E.g. H is, let's think of qubits. Let's do 3 qubits. This is the example of the last lecture. And we could take one, 1, 0 and 0, 1, 1. Okay. Both of these basis vectors have the same occupation numbers. N0 is 1 and N1 is 2. And so does this, the question is, are these two the projected versions of these things equal? So this list of numbers here in this case is 1, 2. Is this definition well defined? Is it the case that this thing equals this thing? This is not obvious. You need to check it. Now in the Fermion case, it's actually, I hope you can almost see straight away how it's going to work. In the Fermion case, we don't have a problem because you may never have occupation numbers above 1. In the Boson case, it takes a little bit more thought, and I'll leave that one as an exercise. That's an exercise for you, just to check that it's well defined, but just look at this example and I claim that you'll already gain a good intuition for how to prove it. In fact, we can do one better. Not only is it well defined, there's even a canonical representative for every n. So after you work out that this is well defined, namely that once you've specified the occupation numbers, it doesn't matter what basis vector you put here. Once you work that out, then you're free to choose one that you like. And the one that we like is the one where we order each of these mu's in ascending order. There's always a permutation that will move these mu's around until they're in ascending order like that, and then we just choose that one. All right, now our task is to work out the normalization Cs of n. We want that these vectors n underline are normalized. That's what we want. Then it could be part of an orthonormal basis. Well, what does this mean? This means that Cs n underline squared that's what that means. So we don't know Csn yet, but we know pretty much everything else. Let's substitute in now the stuff we know. Okay, so the next thing we know, we just substitute in the formula for PS. Remember, PS squared is just PS. And we've got to do that sum there over all the permutations pi and work out what is that number. Okay, well, we're going to have to break this into two cases. As is the case with bosons and fermions, you can't quite do everything in a unified way. Occasionally you have to break out the two cases, but then once you've worked out the answer, often you can summarize things in a very compact way. This will be no exception. Case I. Case I is where s equals plus 1, hence s pi is just 1. It's the boson case, right? Let's look at this sum here. If that's, things simplify dramatically, right? If s pi is just the number 1, I'm going to drop that out, and we have to look at that expression and ask how many times is that 1 and how many times is that 0. When is it 1? When is it 0? Well, it's 1 whenever the permutation pi doesn't change the structure of the basis vector. So I'll do an example. I guess is probably the quickest way to understand this. The problem here is that the actual answer is so compact that it's practically a riddle. So it's better to take some time and do some examples. Let's work with, say, use 6 particles. All right, so this is, we're working with the following basis vector. N is 6. And we've got to wonder how many permutations leave that basis vector unchanged. That's the criteria we have to understand. When is it the case that that equals 1? Well, I hope it's clear when it's equal to 0. It's equal to 0 whenever the permutation moves one of the 1's out of its position. It's equal to 0 when this permutation moves the 3 out of its position, and so on. So it's actually equal to 1 if and only if pi preserves that vector. Right? As long as pi doesn't change the fact that there's 3 1's at the beginning, that there's 2 2's, and that there's a 3, then that'll be 1. If it changes that, however, then poof, it's 0. Now, how many such pi's are there? Well, you're allowed to do anything you like on the first 3 things. You're allowed to do anything you like on the second 2, and you're allowed to do anything you like on the third thing. So there are 3 factorial times 2 factorial times 1 factorial of these guys. Can't write it there, so I'll just move this up to the top. Just leave that there for the moment. So in this case, C plus 1 of the occupation number N1 is 3, N2 is 2, N3 is 1. That's what the occupation number is. So this is just the basis vector. N bar is 3, 2, 1. There's 3 1's, there's 2 2's, and there's 1 3. So we have that squared. Have I lost something here? Ah, there it is. So if we look at this expression up here, 1 equals C. We have that 1 equals this number squared times 1 over 6 factorial. There's the n factorial there. Times by the sum, the number of times that term here equals 1, but we just worked that out. That is equal to n1 factorial times n2 factorial times n3 factorial. in this example. In fact, that's the pattern now of the general answer. Good, we can now write out the general answer. Here it is. In case 1, we have that 1 equals CSn squared times 1 on n factorial sum over pi mu 1 to n. And I can really literally write out the next line, bearing in mind this example. There it is there. That's the answer. It took quicker than the example to write the answer out, but it's practically a riddle until you think through the example. Now, to be absolutely correct, I'll leave the absolute value signs there. Now, there's a simple little observation to make, that n is always equal to the sum of these occupation numbers here. So although there can be an infinite number of basis elements, there can only be at most 6 occurrences if there's n is 6 of different basis vectors. All right, that was case 1, and that's the answer. We have a special notation for these kind of objects. Oh, sorry, I forgot the square root. We have a special kind of notation for this thing here. It's a generalized binomial symbol to the half. Multinomial symbol. That's it, we've worked out the number, we've worked out the normalization. Case 1 is done. We just have to do the Fermion case. Case 2. But the Fermion case, that's super duper easy. Actually, this is sort of a general thing that's true. Although fermions are somehow counterintuitive, calculations involving fermions are super duper nice. As we'll see, you don't get unbounded operators, the Hilbert space is finite dimensional. Lots of stuff goes nicely for fermions. Bosons, although somehow physically more intuitive, mathematically a pain. You know, if we're forced to deal with unbounded operators and nasty issues of continuity. And even at this level, we're going to have to deal with horrible combinatorics for the bosons, whereas the fermions have extremely simple combinatorics. How do we know that the multinomial is finite? If you just look at that note up there, then the numerator is n factorial and the denominator is finite because of this comment in the bracket. It's a good question, but we get lucky. All right, let's do case 2. Well, fermions are super duper easy because each occupation number can only be 0 or 1. I don't think I've written out the proof of that, so I better do that. If n nu is equal to 2 or more, right? If we have an occupation number bigger than equal to 2, then there's we can always find a transposition that just exchanges the two sites or the two locations where the basis vector mu equals nu. Or another way of saying that is that this vector becomes unchanged under u of pi naught. That's sort of obvious, right? But if you apply this particular unitary on the basis vector PS of this, then you get immediately that the vector equals minus itself. Okay, we're in the Fermi case, so P minus 1. You do this sum and redefine the summation variable trick, and you get that this equals minus P minus 1 of this projection there, which implies that it must be equal to 0. Not 0 factorial, just 0. Yeah, 0 factorial. Now that would be absolutely unparsable. Now, that forces us to conclude that n of nu has to be either 0 or 1. Can't be 2 or more, right? Because otherwise the vector is 0. But if n of mu is 0 or 1, then how many permutations leave this object invariant? Remember, this is the central object that determines if a inner product is 0 or not. Well, this only happens when the permutation is the identity. Otherwise, it's 0. Otherwise, you've moved one of these numbers around, and they're all different. All of these numbers are different, right? I didn't write that, but now I will. Okay, there exists. So there exists a permutation such that these numbers are always in strictly ascending order. And then we learn that fact there. So in fact, this normalization in the second case turns out to be extremely simple indeed. It's just 1 on n factorial. And it turns out that this symbol captures both cases. So this multinomial symbol here, the reason I wrote CS there, I mean, even though S was 1 throughout case 1, then this symbol here, this symbol actually makes sense for S as -1. Why does it make sense for S as -1? Because n, this symbol here is this object here, but n of mu is either 0 or 1. 0 factorial is 1, 1 factorial is 1, so that in fact is just 1 on the denominator, and there's a square root of n factorial. So this is actually the correct answer for both the Fermi and the Bose case already, which is pretty cool. All right, I'll just write that out again to amplify that point. I forget the half always. There. So it's the same whether S is +1 or -1. Pretty awesome. So we're a long way towards our goal of working out a basis for HS of n. In fact, we're done. We've worked out our basis for HS of n. It's none other than this n bar.
I think there has to be only n factorial and not.
Oh, yeah. Thank you. There should be n factorial, right? But not on the bottom. Goodness me, it's one of those days. Thank you. That's... right. Now we have an orthonormal basis. N bar is none other than CSN underline PS mu1. There it is. That's our orthonormal basis. Once you have an orthonormal basis, then lots of computations can become easier. One of them is the dimension of this space. Turn to this one here. If you have an orthonormal basis, you just count the basis vectors and you know the dimension of the space. Let's assume it's finite dimensional, right? For this case here, for the dimension of the single particle space is finite dimensional. If the single particle space is infinite dimensional, then there's no hope that this thing will be finite dimensional. It's already dead. Good. What is the dimension of the space here? Well, we're going to do things in reverse order now. We'll do case 2 first and then case 1. We'll definitely see how fermions are simpler to deal with than bosons. Because the dimension of H is not infinity, let it be D. And we ask how many vectors are like this? That's our question. And it's actually, it's pretty simple. We have to choose n things from a set of D things without repetition. That's something that we've, I think you have some experience with. This is a permutation symbol. How many ways are there of choosing n things from the set 1 to D? Well, D choose n. So not a permutation symbol, a binomial symbol. And this is only true for n is less than or equal to D. What happens if n is bigger than D? Then it's 0. And it's 0 because you have to choose n things from D elements, from a set of D elements, but that forces you to choose one of these things twice, at least, right? And then we know it's 0. So this is that's the dimension of this space. Now, the boson case. You can tie yourself in knots with the boson case. I've seen some books spend a very long time arguing the dimension of the boson case. And indeed, at first sight, it isn't a very pretty problem. The number of non the number of orthogonal basis vectors for the boson case is obviously again related to the task of choosing n things from the set 1 to d. But now n can be bigger than d. And in fact, you're allowed to have repetitions. So it's not actually, it's not just a simple object that you've seen before. Well, it is, but getting there is a little bit more complicated. Now, it's the case in combinatorics that often a difficult counting problem can be made very elegant and simple by finding the right representation. And that's what we're going to do right now. Before just sort of banging your head on the problem of choosing n things from the set 1 to d with repetition, then it's worth thinking about how to represent that problem in a way which makes it completely and abundantly clear what the answer is. We're going to use a combinatorial device. This combinatorial device is kind of like using the imaginary numbers to do calculations, to make some calculations simpler. We're going to take our symbols 1 to d, which represent the d possible basis vectors of H, and we're going to adjoin a symbol star to that set. This is super elegant. I just love this. Our task is to count the number of ways you can pull n things from the set 1 to d with repetitions. Well, the way we're going to do it is we're going to take such a choice. You know, there's n11s, there's n22s, there's n33s, there's, in this case, 04s, and all the way up to nDds. And we list the number of times the 1 appears, list the number of times 2 appears, but every time there's a change from the symbol j to j plus 1, we're going to insert a star. And amazingly, it's the stars that matter in counting these choices. Because if I just tell you the locations of the d minus 1 stars, then you can immediately reconstruct how many 1s there were, how many 2s there were, how many 3s there were. So in fact, we're just counting the number of places where I can put d minus 1 stars in n plus d minus 1 places. So I just think that's so cool. And you write out the answer straight away. But I'm going to do some examples because, again, I can write out the answer, but it's a riddle. So let's do, until you see it in action, I think you can't fully appreciate it. right, that's the recipe for constructing the mapping between basis elements and these funny strings. But I'll do some examples. I think once you've seen a couple of those, you'll be absolutely clear on what I'm doing here. So here D is 2, N is 5, and the occupation numbers are N1 is 3, N2 is 2. So the string we associate to that vector, that basis vector, is none other than 1, 1, 1, star, 2, 2. That's the string we associate to that vector. I'll do 2 more examples. Example 1, example 2. Slightly more complicated example, 1, 2, 2, 3, 3, 1. The string we associate with this basis vector three. Oh. The final example, we'll have we won't have all the symbols in our basis set present. N4 has to be 0, thank you, yes. This last example, I think, captures all the complexities of the representation. So to this basis vector here, we associate this tuple here, and notice that where you would have some 4s, there are no 4s, there's just a comma. To every set of occupation numbers like this, there is a tuple like this, and vice versa. These are in bijection, these 2 representations. Therefore, the dimension of our Boson space is the number of ways of putting d-1 stars in n plus d-1 places. Which is a super simple number. It's again a binomial symbol. D minus 1 things, n plus d minus 1 places. That's the answer. You can get to this by other ways, right? You know, dealing with the overcountings without using the star method, but this star symbol is like the imaginary number I. It just really makes this problem completely transparent. Now, there's something kind of interesting that you can do with this number. You can write exactly this number in a different way. This is a perverse way of writing binomial symbols you probably never used before, but it's worth it. I claim that this is very much worth the effort of doing it. I mean, this is indisputably correct, right? If I multiply minus 1 through all these things here, then I get exactly that symbol there. But I'm choosing to write this quantity here in this funny looking way here in order to express a consistent notation for both the boson and the fermion cases. So if you extend the definition of the binomial symbol to negative arguments up here in this fashion, then you actually have a formula that works for both bosons and fermions. Pretty awesome. Oops. There it is there. So S is plus or minus 1. In the fermion case, S is minus 1. Then, yes, exactly, right? In the fermion case, when this is minus 1, okay, no, I've written this wrong. Yeah, that's better. So when in the fermion case minus 1, oh, come on. I think this is finally correct. Is it not correct yet?
What is 0 in the boson case? In boson case it's 0, isn't it?
Yes, it is.
Isn't it minus S?
I think it's minus S to the n, isn't it? Okay, this is, thanks. Let's try again. Third time's a charm. Minus S to the n minus S. I hope this is now correct. So I think that's pretty awesome that you can express the dimensions of these two completely, on the face of it, different subspaces with such a compact formula like this. You don't have to remember that stupid combinatorial symbol up here. Just remember this one, and you know you're going to be right for both cases. Well, that went a bit quicker than I thought. So what I'll do is we'll get already onto our next topic, which is representing operators on our Hilbert space. Very interesting topic indeed. Actually, I suppose before I do that, I will prove to you that I will prove a formula for the dimension of Fock space for a collection, an indeterminate number of fermions. I think that's a formula that deserves to be written down as well. So, what we've worked out so far is the dimension of the n particle subspace. But what we really want to do is now use that formula to work out the dimension of an indeterminate number of particles. And we can do that, right? It is super simple. The dimension of Fock space, Boson or Fermion Fock space, is just the sum of these dimensions that we've already worked out. Assuming the sum converges. That's the formula there. It's obviously infinity if the dimension of H is infinity, so let's focus on the dimension is D case. All right, what can we say about the S is 1 case? The Boson case. What do we know about the dimension of this space for all n? Is it 0? Is it not 0? No matter how large n is, what can we say about the dimension of Hs of n for bosons? The total dimension is infinite, yeah, because each of these terms is strictly positive. Simple statement, right? If I sum an infinite number of non-negative things up, or in fact positive things up, then I get the number infinity, right, in the extended arithmetic. So yeah, if we're going to do extended arithmetic, this is just infinity. Otherwise, it's not defined. Whatever you like, it's infinite. But what about fermions? Now, this is pretty cool, right? Fermions. We can simplify things a bit for fermions. I've got this encrypted notation here, but we can make this life a lot easier, right? Because we know that when n is bigger than d, this term, this dimension is actually defined to be 0. So this is the S is minus 1 case. Now this number this is a known number, it's 2 to the n. Now, there's various ways to remember this. One is just to remember this. But another way, which I really like, is that you can prove this by only knowing about Pascal's triangle. So why is this 2 to the n? Well, let's imagine expanding out 1 plus 1 to the power n. All right, so that's 2 to the n is 1 plus 1 to the power n. And we know how to do these binomial expansions. All right, that's 1 to the power n d, sorry, 0 choose n, 1 to the power of n, 1 to the power of 0, plus 1 choose, I got it the wrong way around again, haven't I? It's d, choose 0, 1 to the d, 1 to the 0, plus d, choose 1, 1 to the d minus 1, 1 to the 1, plus d, choose 2, 1 to the d minus 2, 1 to the 2. Poof, there it is, proof is done. So it's a neat little way to remember that the sum of these binomial coefficients is 2 to the n. So that just about wraps it up. The dimension of Fock space for n or fewer fermions, where the emphasis is on the not knowing how many fermions you have, is at most 2 to the n. The dimension of boson Fock space is infinite. And therein we see the real fundamental difference between fermions and bosons, and the thing that makes life so much more difficult for bosons than for fermions, because infinite dimensional Hilbert spaces are tricky. And in fact, the real way to deal with bosons is to forget the Hilbert space altogether and work with the observables. And use tools from von Neumann algebras instead. And C-star algebras. It's extremely tempting to do that theory here, and I'll do it by proxy, actually. I will sneakily do a bit of C-star algebras to talk about bosons in this course, but we're not going to go through all the gory details of topological vector spaces. It should be 2 to the d. Thank you. Yes, it's ever so tempting to write n. Goodness me. Thank you. If you have n things, you just want to write down n. N stands for number. Maybe it's not so difficult in German, actually. Nummer. No, it's just as bad, isn't it? All right, let's get on to operators now on this vector space. So we got this vector space, gamma S of H. Very well, we have a vector space. We want to talk about observables, though. In any good statistical theory, what you really have to specify are the observables that correspond to experiments. And, okay, for fermions, this Hilbert space is finite dimensional if H is finite dimensional. But for bosons, it certainly is not the case. And this is kind of awkward, right? If you want to talk about experiments that presumably use finite resources, you don't want to be specifying an infinite number of things every time you want to talk about the experiment. So you need to find a way to specify an infinite number of things in a compact way. I'm going to show you such a way. I'm going to introduce a convenient set of operators which we have good reasons to think correspond to actions we can take in an experiment, and B, which can be specified with a finite amount of data. Turns out that you can build Fock space, this somewhat complicated infinite direct sum in the case of bosons, by successively applying certain operators called creation operators. You've seen them before in the context of the harmonic oscillator. Now we're going to introduce them in their full generality. And creation operators work by first specifying a state of the single particle space. So phi is a single particle state. And we choose some vector psi in our full Fock space. And I'm going to write the action of a creation operator on that vector psi for all psi and for all phi. It's a little bit awkward. I'm going to specify what AS dagger of phi looks like once you've applied it to psi by saying what it looks like on the n particles subspace. We always have this case distinction, the zero particle space, the vacuum sector. What is AS on the vacuum? A dagger S on the vacuum. But the way I've been doing things, I've been doing it like that. That's the creation operator right there. You have to check that it defines an honest operator on this Hilbert space by extending by linearity. And once you have this definition, we can start working out consequences of this definition. I see that I'm running slowly out of time. I'll write down one thing, two things we can say about these creation operators. The first thing I write down is an identity which should convince you that you can build every basis vector in Fock space by applying these creation operators. And the second thing is an exchange relation, which captures the boson and fermion statistics. Now, let's think about applying AS twice. What if we apply AS to our Hilbert space and then AS again? Let's find out what happens. That's the result of applying the creation operator twice. It's an identity. That's an exercise. In fact, a lot of this stuff I'll just leave as exercises because they're small, quick computations that give you some insight into what's going on. And that means that if you want to build a basis for Fock space, well, we know how to build a basis for Fock space. What we do is we just choose a basis for our single particle space and apply projections to it. But another way of building a basis for Fock space is simply by applying creation operators for those single particle basis elements n times. So this should, I hope, convince you that you can build basis vectors from the vacuum state, omega, by applying these operators AS in succession. That's the first thing to note. So this is that's essentially the proof that these creation operators can construct a basis or construct all the Fock space from a single state. And the thing that I want to end on now is another identity. It's very simple. And that is the exchange relation. And it's probably this relation here that you're most familiar with in the context of bosons and fermions. It says that these operators commute when we have bosons and anti-commute when we have fermions. You've no doubt heard this before in some context. Good. I think we'll stop here. This seems like a convenient moment, and we will continue in our next lecture. Thank you very much.